Let's start taking an unknown molecule that you want to identify. There are plenty of analyses you can perform. You maybe will start with a mass spectroscopy to know the mass of the molecule, then an elemental analysis to know the element of which the molecule is made, and then maybe you will move with an infrared spectroscopy technique to know the possible bond inside the molecule, and if you're lucky, taking all together, you will be able to identify it. These are a lot of analysis, and even for the simplest molecule can be tricky to understand the exact conformation without any doubts. It would be nice if there is just one single technique that it's able to give to you all the information you need to identify an unknown molecule. Maybe a technique that have a privileged point of view. For example, the nuclei point of view that can ask to each single nucleus, what are you seeing around you? And that technique exists. It's the nuclear magnetic resonance. But working with nuclei, it's not simple. Many analytical techniques just monitor the transition between energy level. And nuclei have well-defined energy level, but their energy involved in this transition is enormous. We are talking about gamma rays, and this is the typical ionizing radiation you are thinking about when you hear something with nucleus or atomic in this name. That's not our case. In physics, all particles have one fundamental property. That is the spin. Usually it's just represented like a sphere that it's rotating. Spin is always represented with just one number that can be an integer number or a half integer number. You probably already know that electrons have 1/2 as spin. That's why while you populate in the orbitals, you put 2 electrons in each orbital. Usually you represented them with one arrow up to indicate the plus 1/2 spin and one arrow down to represent the minus 1/2 spin. But particles can also have spin of 1, so you have 3 possible energy level, 1, 0 and -1, and so on and so forth. But spin have one major issue. These are usually degenerate states. That means that they have all the exact same energy, and if they have the same energy, you cannot monitor the transition between energy level because the system can just flow between different spin states. But we can solve this problem with a magnetic field. This is called Zeeman effect, and that means that when you put your system in a magnetic field, you just reduce the energy level of some spin state and increase the energy level of other spin states. And in that way, you can monitor the transition between them. And this is what we do. We want to monitor, yes, the nuclear transition, but between spin states whose degeneracy has been resolved thanks to a magnetic fields due to Zeeman effect. This explains why it's called nuclear magnetics. On the resonance we will see later. And before you ask, yes, this technique is closely related to the magnetic resonance imaging used for diagnostics. And in that case, for the same reason I said about the nuclear words, it's just been missed. So people will not think about anything extremely dangerous. In fact, the Zeeman effect is quite weak. Even with a very high magnetic field, we are still working in the radio waves, so very low energy radiation. But not all the nuclei are the same. First, we have to look at the mass number. If it's even, then the spin is represented by an integer number. And if it's odd, then the spin is a half integer number. That also divides the particle in bosons with integer spin and fermions with half integer spin. With just this simple fact, you will understand that NMR is isotopic sensitive, and that's why you will hear a lot of words like natural abundance or enriched samples. Let's go first with bosons. These are the more problematic. Now look at the atomic number. If it is even, like for carbon-12, then the spin is 0. If the spin is 0, it means that there is only one spin level, so no degeneration, no transition between spin level. That means that it's impossible to use NMR to analyze these nuclei. And as I say, carbon-12, that it's the most abundant isotope of carbon, and it's a problem. These are also referred as spin-inactive nuclei. So what happens if the atomic number is odd with mass even? Well, in most cases they are just radioactive isotopes, so not very stable, with only 5 exceptions. Hydrogen-2, also referred as deuteron, lithium-6, boron-10, nitrogen-14 and tantalum-180 metastable. No one ever performed NMR on this isotope of tantalum, but it's in the list. There are also other 4 isotopes that are stable enough to be handled safely, but yet it's problematic. So let's go with the fermions. Well, even in this case, it's not so good. The 1/2 spin is the preferred one. Any other nuclei with spin 1 or above, it's also referred as quadrupolar nuclei. And in this case, you have weird interaction, weird behavior. So if it's possible, you will avoid to work with this nuclei. So at the end, the best nuclei to work with are just 30, no more. That doesn't mean you cannot work with any other spin-active nucleus, but it's just it needs more careful preparation and sequencing and other things that we will see later. So from an organic chemistry point of view, what's our position? Hydrogen-1, enormous natural abundance, spin 1/2, we are okay. Carbon-12, we already see it's not good, so we have to go with carbon-13. That, yes, it's spin 1/2, but a very, very low abundance in nature. So maybe you will go for an enriched sample. Nitrogen-14, big natural abundance, spin 1. So you will probably go with nitrogen-15, that it's very low natural abundance, but spin 1/2, so better to work with. Oxygen, well, oxygen-16, spin 0 and enormous natural abundance. You have to go with oxygen-17, but it's spin 3/2, so you have to work with a quadrupolar nucleus. So we are in an optimal position for protons, not so well for carbon or nitrogen, but we can always enrich the sample or acquire for longer period of times or other peculiar technique to take the signal of these nuclei. So let's focus for a moment on 1/2 nuclei. Now, the model that I'm going to introduce in this series of video, it's called vector model, and it's a semi-classical model. That means that it's trying to explain in a classical way a quantistic effect. So it's not perfect, but I think it's very good to explain what is happening, even if it's not exactly what is happening. And also it can be applied only to 1/2 nuclei, that what we are more interested in. So we take our nucleus, we put it in a magnetic field, and so some spin level go down, so they get more stable. The other spin level, it's destabilized, and so it increases its energy. Which level it's going up and which level it's going down? Well, depends on the nuclei. If the nucleus is paramagnetic, then the most stable spin, it's the spin up, while the destabilized level, it's spin down, so -1/2. But if we are working with a diamagnetic nucleus, well, in that case, the most stable state, it's the down state, and the energy level destabilized, it's the +1/2 or up state. Now let's focus only on the paramagnetic nuclei. Then the diamagnetic are just the same things, but the other way around. The system that usually it's half in spin up and half in spin down and can freely move between these two states. Now they prefer to stay in the up states than in the down state. That means that now our system is polarized with a total magnetization that have the same direction of the magnetic field. Usually we put the magnetic field along the z-axis in the positive direction. But this is not the only thing that is happening to the nuclei, but we will see it in the next video.